In this lesson, we're going to look at transmission diffraction gratings. We're going to talk about what they are and how they work. And they're very similar to the double slit experiment and the concept behind that we covered last lesson. Outcomes for today's lesson are listed here. Some of it is repeating that d sine theta equals m lambda. We're going to talk about in a little bit more detail. We'll use it again. And a lot of this will come up very, very similar to how it did with the double slit. The diffraction grating. A diffraction grating is effectively a very large number of narrow slits arranged so that they're all parallel to each other. We often make these by scratching lines on glass. This is done very specifically with a laser, not just getting a scalpel and just gouging in grooves. It's done very, very specifically. So this representation here gives you a bit of an example. You've got these little scratches here in the glass and they're all evenly spaced and very strategically done. The lines that are done make the glass or plastic opaque. So light doesn't pass through these lines, but it will pass through the transparent plastic or the glass in between them. So the lines create the same effect as having lots of different slits by doing this. An example of a diffraction grating is shown here. I'm giving you the answer above. So in this example, the first window consists of 100 lines per millimeter. So there's 100 little scratch lines in there for every single millimeter. This means that the distance between the slits is 1 millimeter divided by 100 lines, and I get 1 times 10 to the minus 5 meters as my distance between slits. If I was to use the same process, what is the distance between the slits in the third window, where I've got 600 lines per millimeter? And the answer, which is already on the screen, would be 1.67 times 10 to the minus 6. So it's important that you know how to do this. If I just say how many lines per mil, therefore what is the distance between one line, it's fairly straightforward. When we have parallel beams of monochromatic light and we direct it at a right angle to a transmission diffraction grating, which is really just lots of slits. It's a fancy way of saying lots of slits. The light that's transmitted produces a very narrow, intense, bright line, or a maxima as we call it, which is separated by large regions of negligible intensity or darkness. So we get this same sort of interference pattern that's very similar, with some differences. The image on the left shows the interference pattern if we were to use a laser. Because it's a monochromatic source, we just get these little dots. And on the right would show if we used something else, like a green light source. So we filter it or something like that, or it's passed through a transmission diffraction grating. We get these lines of color, of maxima. In both cases, the maxima are narrow, they're intense, and they occur at large angles as well as just being in front. And the large angle thing is important. We'll talk about why that happens a little bit later. Just as with single slit, double slit interference produces this maxima and minima, and having multiple slits, which is our diffraction grating, produces a continual band of interference patterns with some differences, such as a maxima at much larger angles. When we have parallel beams of light, which we call wave fronts, and they hit a diffraction grating, the light is in phase as it passes through the slits. Given that the slits are very thin, and the width is comparable to the wavelength, we get diffraction that's producing at each slit. So we get these circular wavelets that you can see here. The smaller the slit width, the more the light diffracts because we're getting closer to that wavelength of light that we're using. All of these circular wavelets overlap and therefore they're going to interfere in some way. Just like in the previous video when we talked about the two balls, or if you talk about two splashes in the water and the ripples cancel out, you're doing the same thing, but you're adding like multiple balls to bounce on the water. Why do we get these maxima at large angles? This is a unique concept to the diffraction grating. If we have light passing through the grating, and it's passing through all of these little slits, the light reaching the center of a screen is going to produce a maximum, which is just a singular form of maxima for the language. Because just like the two-slit interference, the light reaches the center of the screen in phase and therefore undergoes constructive interference. As we move away from the center of the screen, however, the path difference is increasing. So the light from adjacent slits starts to become out of phase. And remember, the more out of phase we are, the more it destructively interferes. If you're out of phase by lambda on 2, half a wavelength, it completely cancels out and you have no light there. Given that we've got so many slits on a grating, there are always two slits for which the light is half a wavelength out of phase. For instance, what I mean by that is, if the light from an adjacent slit is only slightly out of phase, and let's say it's 1/100th of a wavelength out, then that first slit will be half a wavelength out of phase from the 51st slit, because if it's 100, 50 is now half a wavelength. And the light from the second slit will be out of phase with the light from the 52nd slit, and so on and so forth. So because I've got so many slits, there's always something with the tiniest amount of phase difference that 50, 60, 100 slits later, something else is out of phase by lambda on 2. All of these half wavelength slits, so like 1 and 51, will undergo destructive interference and the light will be low, or it may be negligible, so I have a dark spot. The intensity remains negligible until the path difference increases back to 1 wavelength. So I might be 1 and 51 cancel out, and it might take 25 more slits to get back, or another 50 slits to get back to the full wavelength, and I constructively interfere again. At this point, the light from the adjacent slits interferes constructively and we get that maximum. Similarly, as the path difference increases beyond 1 wavelength, the intensity is once again negligible until it is exactly 2 wavelengths. So until we get these whole wavelength shifts, we don't have our bright spots. The first assumption we need to make is of a large distance to the screen compared with the slit separation. We also assume that the light rays are parallel. So what we mean by that is if you take a distance and we call it more or less like an infinite distance, light rays all become parallel to each other. We know in the real world that's not actually going to happen, but given the distance is so massive compared to the slit separation, they basically act as parallel rays. So just like our picture here, the interference pattern is symmetrical. So this is our theta equals 0 angle. This is our central line where we get the brightest spot. We're interfering. Suddenly we're a whole wavelength. Then we're interfering again, a whole wavelength or multiple wavelengths, we get a bright spot. So the intensity is going to decrease as you go further out. The center is always the brightest spot, but we get a slightly less bright spot, slightly less bright spot, slightly less bright spot, so on and so forth. We often represent this using thin lines, which we see on the right, rather than trying to draw a full intensity graph with very skinny gaps. It's completely fine to do it. We'll just do these lines. We know that it actually would look more like this intensity graph. It's not just on-off, it's gradual, but we just do it for lines because we're lazy and it's much easier to draw. So what about that negligible intensity between the adjacent maxima? If we were to consider an angle which is only slightly different to one of the maxima, so the OPD difference of, say, lambda on 20. The phase difference between rays 1 and 2 would be very small, as would the phase difference between rays 2 and 3, and rays 1 and 3, because the difference between them is tiny, so I haven't shifted it by much. However, rays 1 and 11 would be out of phase by lambda on 2 now, and these would cancel out. Similarly, ray number 2 and ray number 12 would also annul, as will rays 3 and 13, and so on and so forth. All of these rays are going to annul each other pairwise, and there will be negligible intensity at these angles. So just like we talked about before, these pairs that are lambda on 2 out are going to cancel. This is true for all of the angles except where d sine theta is back to equaling m lambda, a whole integer. So once we've cancelled out, and suddenly that wave, the path difference between the two waves is a whole wavelength again, I get a bright spot again. So we can see a really good explanation of that here. If you wanted to watch this video, this is a great explanation of that with a little bit more detail. But if you think about, if this is only, let's say like 1/10 of a wavelength, then 5 down, we're 5/10 of a wavelength, so we're half a wavelength out, it's going to cancel. But that'll cancel with the next one, and the next one, and the next one. So it's not until we go a sharp enough angle that the path difference becomes great enough to actually be back to a whole wavelength. And that's why we get these bigger and bigger gaps as we get further and further out, because you've got to travel a lot further before you get a whole wavelength out every single time you shift that angle. Okay, so some practice questions talking about diffraction gratings. Just like I talked about before, we've got a diffraction grating consisting of 3,000 lines per centimeter. Calculate the distance between the grating lines. Calculate the angle of the third order maximum. So remember, this is just the m value using our formula from before. Determine the number of lines. So we've gone backwards. So how many lines do we have in this grating? And then again, maximum number of orders possible for this diffraction grating. So this question's a little bit different. Have a go at these. I'll be back in a minute. Alright, let's see how we did. So in the first one, we're using we want to find D, so we look at our 1 times 10 to the minus 2, divide it by the number of slits, 3,000 slits per centimeter, centimeter to meter, we get 3.33 times 10 to the minus 6 meters between the grating lines. Then the next one, we use our d sine theta equals m lambda. We're third order maxima, so m is 3. We get 37.8 degrees. Number of lines per meter on the diffraction grating. Again, we've got to tweak this a little bit. We start with our d sine theta, figure out what the distance is, what d is between the lines. Then if n represents the number of lines per meter, d is 1 over n. So just like in the earlier example, we could have written this as d is 1 over n. One line, or the distance we've got, 1 meter, divide it by how many lines per meter, for example. We get 6.66 times 10 to the 5. That's how many slits, lines we have on the diffraction grating. Last one, we use d sine theta, we get our m value, which is our maxima, we get 4.9. So really we can't have 4.9, you can't have decimal places, and we can't round it because if we don't have a fifth one, we can't just say, oh, well, 4.9 is 5. It's not. So you can only take the whole maxima. So we're going to end up with 4 in this case. So the maximum angle, or using that angle that we can have, we're going to have 4 orders. So d sine theta, 90 degrees is the furthest that we can go. If you think about it, we can't go beyond 90 degrees. We're going to start be like curving around the corners and things. So when we do that, we just use our 90 degree factor. D we knew, and lambda we knew. So what happens if we use white light? In the earlier video, in that double slit experiment, they sort of briefly touched on it, and if you watch the video by Veritasium where he makes his own giant diffraction grating that he can just carry around on the beach, he's using white light there. So what happens if we use white light? When white light is shone through a diffraction grating, the central maxima is going to be white, as every color reinforces at the center of the screen because d sine theta equals 0 for all wavelengths that make up white light. There will be an annulment, a darker area, on either side of that central maximum though. Following this area of annulment, there's going to be a continuous spectrum of colors. The colors are going to range from the smallest wavelength of violet, so the smallest theta, closest to the central maxima, and out all the way to red, where we have the largest wavelength. Higher order spectra are also formed further out from the center. The spectrum of each order, however, will be fainter and more spread out than the one before it. After we get to about 3 orders, the spectra of the orders will start to overlap. So it looks a little bit like this. We've got our bright spot, we've got a dark pattern, we end up with our violets and our blues, go all the way out to red, dark spot, same sort of thing again, and we're going to start to have more and more overlapping outside of this phase. But we basically get our spectrum colors. So we go white, spectrum, black, spectrum, so on and so forth. So that's our white light pattern. Because of the frequencies and wavelengths of each color, that's why we're going to diffract and interfere at slightly different phases. So based on smallest to largest, we get this diffraction over different angles. So if we look at this, note that red has the largest wavelength, and therefore it's going to have the largest angle for its maxima. So that's why red is the furthest away at the largest angle. So right in our 0th maxima, m equals 0, we get all colors maximum. And if we have all colors the maximum, they're all constructively interfering, we get white light. Then as we diffract out and we interfere, blue constructively interferes here, the first, then we get red, then we get our dark spot as they're all cancelling out, then we go back to our blue, and then red, and so on. So one of the things that you're expected to be able to do is identifying the properties of a diffraction grating, which make it useful in spectroscopy. So what is spectroscopy? Spectroscopy is the science of analysing the chemical composition of substances from the spectra associated with them. Basically, it's using light, using what we've talked about and what we're about to talk about to identify what things are made of. That's what spectroscopy is. Hopefully, you can think of a few reasons why this is useful. If not, I'm going to give you some more. But it is an extremely useful thing in discovering science. So in order to do this, this involves measuring the wavelengths of light, which is produced by the substance that is emitting it. As we've seen, we can use this diffraction grating to find the wavelength of the incoming light, just by measuring the difference between their interference fringes and the distance from the slits to the screen. We can rearrange and we can find the wavelength of light. We can also do this using a prism, but to use a prism requires the measurement of several angles and much more complex calculations. So the double slit or the diffraction grating is a simpler version that still gives quite good results. The following properties of a diffraction grating are what makes it useful for spectroscopy. The grating lines are close together. This means that the maxima are viewed at very large angles. So if the grating lines are close, the maxima get bigger. The angular position of the maxima can be measured precisely, as the experimental error is smaller compared to their spacing. If they're all really small, say they're like all within a millimeter, it's very hard to measure something that's within a millimeter because now your error, which is maybe half a millimeter, is more than the measurement you're taking. If you can blow it all the way out to 30 centimeters and your uncertainty in the measuring apparatus is 1 millimeter, that's fairly negligible compared to the actual measuring gaps. So it makes it a lot more accurate. The maxima are thin, intense lines rather than bands. The error involved with judging the center is small as a result of this. So if we can get really thin, intense bands rather than like a gradual phase, it's really hard to say, well, where do I stop my measurement from in that case? So we want the grating lines really close together, which gives us maximum or large viewing angles. We want the maximum to be thin, intense lines rather than gradual bands. There are significant properties that make it useful. We need those two things in order to be able to actually use it. So, an example. If we have a grating spectrometer and it's used to view sodium light using the transmission grating consisting of 5 times 10 to the 5 lines per meter. The first order maxima is viewed at an angle of 17.1 degrees. Calculate the wavelength of the sodium light. So I'm just going to show this one to you. I'm not going to give you any time. If you want to, pause the video now and have a go at it. So what they've done is they've said the distance is 1 divided by 5 times 10 to the 5. Figure out this is our distance between slits, 2 times 10 to the negative 6 meters. Then we plug that into our d sine theta, and we rearrange for lambda because this is what I want. Calculate the wavelength. D sine theta, I know D, I found it. Sine theta, 17.1 degrees was the viewing angle for the nth being 1, the nth maxima. So I plug that in, 17.1. That's equal to the wavelength times 1, and I get 5.88 times 10 to the negative 7 meters is my wavelength. So this is an example of how we would use it by using the measurements that we've taken. This example is an alternative method for determining the wavelength of a laser light. They've got the diffraction grating, it's got 3000 lines per millimeter. They've shone a helium neon laser through it. The laser is placed 1 meter from the screen. Remember, we want the screen to be significantly longer than the distance between the spacing so that we can get those parallel rays. And they take a third order maxima, a distance of 69.5 centimeters from the center. So again, remember, that was one of our important characteristics for spectroscopy to be useful. We need that distance to be large, so we get a large viewing angle, which reduces our error in the measurements. Calculate what that angle is. To do that, I do a bit of trigonometry here. I know this length, I know the distance here, and I want the angle, so I can use tan theta, opposite over adjacent, and I get 0.695 divided by 1. Remember, we want meters, so they both need to be in meters. 34.8 degrees. That's the angle of my third order maxima. Calculate the wavelength. Now that I know my theta, I can use my d sine theta. I need the d first, so I plug that into d sine theta equals m lambda. And in this case, choose which maxima you want. We're using third order, or you can use first order. You're going to get your wavelength.